Okay, great. Okay, so really I want this seminar to sort of be of use to people who perhaps are doing some X-ray spectroscopy. And if there are people out there that are already doing X-ray spectroscopy, there is a good chance that what they're doing is K-edge X-ray absorption spectroscopy on something like transition metal ions, for instance. So one of the things about doing X-ray spectroscopy of that type is that actually the absorption edge is jumping over the Fermi level, or in other words, what you're accessing are not the frontier molecular orbitals. So this has sort of a somewhat of a limitation in understanding electronic structure, since really by probing those lowest unoccupied molecular orbitals or the Fermi level, you're actually directly accessing the electronic structure, which is pertinent to activity or magnetic properties, for instance. So here is a picture, typical picture of a iron K-edge Zane spectrum. So out here we have these wiggly lines related to the XAFS, and then we have the absorption threshold, which is a transition exciting a 1s electron into unoccupied 4p. And what I'm interested in here is this tiny little peak known as the pre-edge. So what I want you to be able to get out of this talk is how to look at your data and start making use of these pre-edges that might be, for instance, coming free with your XAFS. And then I'll also go on to some other edges which directly probe the this lowest unoccupied molecular orbitals or Fermi levels directly. So going into a bit more detail about this, this iron K-edge example, we have the pre-edge, as you can see, being much less intense than the main edge, which is, of course, the transition into the 4p. So the reason for this is due to transition selection rules. The dipole transition oscillator strength is much greater than that of the quadrupole. So we, as we go from an S to a P, we change an orbital angular momentum of 1. Whereas if we go from an S to a D, that's a change in the orbital angular momentum of 2, and therefore we have a much weaker intensity. However, for most spectrometers, you can still get pretty good data quality down here. And with the arrival of high energy resolution fluorescence detected spectrometers, one can get very good resolution in this region too. So it's worth spending some time to understand how to interpret these parts of the spectrum. So another thing worth noting is that often, and I'll just jump back, this pre-edge region and beyond the pre-edge region, the rising edge, is often used as a means to quantify oxidation state. So as you reduce the ion that you're probing, so say iron 3 to iron 2, you'd expect this absorption threshold to decrease in energy. And therefore you can use this as an empirical way of tracking changes in oxidation state or comparing different samples to discern what oxidation state might be. However, what I'd also want to add is that this pre-edge region is extremely valuable for doing such quantification of oxidation state too. And there are a few limitations in the use of this rising edge for oxidation state determination that I'll outline as follows. So this absorption threshold can often be sensitive to other factors, and I'll just give 2 recent examples from my research. Here's one example where by a change in coordination symmetry, so initially this is actually half of a ferric, so iron 3 plus high spin dimer. And if we have I've just taken 1/2 of that unit here, just for simplicity. Initially in this spectrum in red, we can, this fairly octahedral coordination environment gives rise to a rising edge like this, shown in red. And then if we compare that with something where one of these oxo bonds has got a lot shorter, so we've gone from a octahedral, qualitatively octahedral coordination environment to a C4V environment, then we can see quite a severe downshift in the rising edge. However, we've not changed oxidation state. So this could be falsely interpreted as a change in oxidation state, where really that is not the case. Similarly, here on the right-hand side, I'm showing a spin crossover system. So a system which, with respect to temperature, has changed from being high spin to low spin, and you can see again a large shift in the rising edge, which could be misinterpreted as a change in oxidation state. There are things going on down here at the pre-edge, though, and these can be much stronger fingerprints for oxidation state, and also carrying a sensitivity to spin. So let's look in a bit more detail about how we can directly target frontier molecular orbitals. So this is the periodic table of X-ray spectroscopy provided by Berkeley. And I'll just identify different regions. So I've mentioned the K pre-edge. So the K pre-edge is good for accessing the directly lowest occupied molecular orbitals for transition metal ions, or alternatively, we can use the L edge. For the F block, it's the L pre-edge, which, if it can be resolved, is a good way of accessing directly lowest occupied molecular orbitals, and the M45 edge. And finally, also ligand pre-edge. So if your transition metal ion, for instance, is coordinated to a ligand, of say chlorine, then it's possible to measure how the chlorine engages in bonding with the ion, and that's observed in the ligand pre-edge. So ligand pre-edge is outside of the scope of this talk, and really what I'm going to be focusing on are the K pre-edges and L edges of first row transition metal ions. So here's the overview. So I'll be giving an introduction to the measurement and analysis of frontier molecular orbitals, and I'll do this, as I've said, with transition metal K pre-edge analysis initially. So I'll discuss K pre-edges for octahedral sites, and then make a brief introduction to lower symmetries. And then after that, I'll finally cover some L23 edge X-ray absorption spectroscopy and analysis for first row transition metal ions too. Okay, so let's start with some data. So as I mentioned at the beginning, I gave this scenario where perhaps you've gone to the synchrotron to measure some XAFS because you're interested in coordination and bonding, and perhaps also you're interested in oxidation state. So you've gone there with the view of using the rising edge to discern what the oxidation state of your metal ion might be. What I want you then to consider is this part of the spectrum, the pre-edge. So we zoom in, this is what the pre-edge looks like. So we can do our standard Zane's XAFS analysis, where we do a post-edge normalization to 1 with a background subtraction using, say, splines or something in order to get a nice flat post-edge. Then we can look here with this normalized units of intensity, this pre-edge region. And then as a first step, what's interesting is to do a peak deconvolution. So for that, we will do some peak fitting. So there are various softwares to assist in doing that. The line width of the pre-edge is typically that of a convolution of Gaussian and Lorentzian broadening. So one can use a pseudo void in order to fit that. And here you can see this is actually for iron 3+. We've got 2 features that can be resolved at the pre-edge. Okay. So what are those 2 features? Well, if we just consider the crystal field, well, we have an octahedral splitting. So put my laser back on. Have an octahedral coordination environment. We have our metal ion in the beginning, and then we have 6 core bonds around the outside. So just negative point charges. We can consider these as within a crystal field model. Now, the 3D orbitals that overlap directly with the axes that correspond with ligands, of course, going to feel a destabilization in their energy. So in an octahedral crystal field, this pushes the 3D z squared, which runs along the z-axis, and 3D x squared minus y squared, which slopes points along the ligand atoms in the equatorial plane. And this is raised relative to the xy, xyz, and orbitals, which have their lobes pointing away from where the negative charges are of the ligand atoms. So this splitting here is what we call the crystal field splitting, or ligand field splitting, if we can't start using a crystal field model to fit to some experimental data. And this splitting here is often known as delta or 10dq. So if we come back to understanding our K pre-edge, then we can simply consider the 1s excitation into our 3D shell. So initially this is iron 3+, so we have a 3d5 electron configuration. So these are the EG orbitals at higher energy and T2G orbitals just below, as I explained on the previous slide, split due to the crystal field 10dq. Now, the 1s excitation can bop a single electron into the T2G orbitals, and we have three holes to accept a 1s electron, or we could bop an electron into the EG orbitals, and we have two holes that can receive that 1s electron. And what this gives rise to is a 3:2 intensity ratio in the pre-edge, where the splitting between these two is 10dq. Very simple. Now, importantly here, this shape is directly characteristic to the oxidation state, of course, because the oxidation state is simply the number of electrons in the d shell here for this first row transition metal ion. And also we learned something about bonding, since we were able to deduce this energy, which is the amount the d orbitals are split. Okay, let's try another case. Well, now instead of just doing regular Zanes, I'm taking an example where high energy resolution fluorescence detection has been conducted. And since there isn't really time to discuss that, and it's been covered once before, if you're not familiar with high energy resolution fluorescence detectors, you can see a previous webinar by Peter Gletzel, link at the bottom. So here for cobalt-2, we've got a 3d7 ground state, so T2G 5 electrons in the T2G and 2 electrons in the EG. So we might expect from the previous example to have 2 excitations, one where we have a 1s electron going into the EG, and another where we have a 1s electron going into the EG. However, this is what the pre-edge looks like. This is a pre-edge at slightly higher energy resolution because we've used this Herf's method, but it's still a 1s to 3D transition. So if I do a peak fitting deconvolution of that, I see, in fact, what we experimentally observe are 4 peaks. So how do we interpret this? So to interpret that, we could now start to consider the full electronic structure Hamiltonian for 3D ion. Now, if we look at this in its entirety, it looks fairly cumbersome. And if we were to solving this in a semi-empirical way, we'd have lots of free parameters. If we're to solve this in an ab initio way, then it's extremely computationally intensive. However, if we just want to understand the shape of this pre-edge region for the transition metal ion, there are several terms we can neglect. So first of all, if we're not interested in the energy of this, this transition, then we can ignore the electron kinetic energy and the effect of the nuclear charge. And if we consider for a 3D metal ion that, as is most often the case, the spin-orbit coupling is quenched by the crystal field. So this means we can essentially neglect spin-orbit coupling too. So what we're left with are the electron-electron interactions, so DD electron interactions, and the effect of the crystal field, which I pictorially explained just before. So first of all, let's consider electron-electron interactions, known as the multiplet effects. So this was the term that I showed on the previous slide, and really what this is considering the interaction between pairs of electrons, and where we can consider this as a matrix where we label the pairs of electrons in accordance with their symmetry using term symbols, this problem can be broken down into two parts by taking the radial and spherical parts individually. So here what we have are angular parts to this model, Fk and Gk in lowercase, and the angular part is has an analytical solution, and it's given by what are known as the 3J and 6J symbols. And then the radial part, which is a number known as the Slater integral, which can be computed from ab initio theory, at least for a first approximation. And then we have beta. Hello? Oh, I think somebody said something, but that was probably a mistake. If anybody has questions, they're welcome to ask them directly, since I don't have a view of the chat. So beta is a scaling factor, and that enables us to scale what the Slater integrals obtained from ab initio theory, that enables us to scale those to experimental data. So the angular part, yes, for a 3D ion, this has an analytical solution such that Fk is equal to 0, 2, or 4. So that part's simple. And the radial parts, the Slater integrals, they're constants that obtained from ab initio theory. And typically we would use Hartree-Fock theory. And most multiplet codes have the Slater integrals obtained from Hartree-Fock theory readily calculated. So the aim here then, in terms of a free parameter, is then a matter of scaling what is obtained from ab initio theory to the experimental data. So that's the electron-electron interaction part. Finally, the crystal field part, which I covered a moment ago. So this is an expansion on normalized spherical harmonics. And we have a crystal field parameter, which can be written as AKM. However, for octahedral symmetry, there in fact, the AKM values are all 0, except for A00 and A40. And this then can be written out as follows. So this is the energy of the EG orbitals and the energy of the T2G orbitals. And this is rewritten in terms of dq traditionally, where the ET2G is at -4 dq and EEG at positive 6 dq. So that gives us our total 10 dq splitting. All right, so it seems a little bit complicated, but ultimately I think the conclusion is that this is a numerical calculation. So we're going to use some software in order to actually calculate these energies and spectra potentially. And there are two free parameters for a octahedral compound. So for simulating the pre-edge flux, one is the what I've called here is beta. And that is the scaling factor to the electron-electron interactions. And the other is the crystal field parameter, which A40, or what is more commonly referred to as in terms of DQ. Notice I've also grayed out the interaction between shells. So this part of the electron-electron interaction is concerns between 3D electrons. The interaction between the 1s electron and the 3D. So in the absorption final state, we have this 1s 1 3D n plus 1 configuration. So that 1s electron, in principle, has an exchange and repulsion with the 3D ion. However, this is negligibly small, so we can ignore that. So these are all the approximations that I'm summarizing, the approximations that I've mentioned along the way and talking about this Hamiltonian. So if we just limit ourselves to being concerned with the spectral shape and not the energy, that means we can knock out this kinetic energy nuclear term. We can consider, as I just mentioned, if the 1s core hole and to 3D valence interactions are negligible, we can knock out the intershell exchange and repulsion. Also, if we assume the 3D spin-orbit coupling is quenched, that means we can knock that term out too. And also, let's ignore minor variations in coordination symmetry. So as long as our system's 6 coordinate and all the bonds are approximately of equivalent-ish length, then we can assume that just having one crystal field parameter, 10 will be sufficient. So there we have it. We have 2 free parameters. So often the way in which this Hamiltonian can be, this simplified Hamiltonian can be evaluated, where we just have 3D electron interactions in the crystal field with that of a Tanabe Sugano diagram. So you may have seen these in talks of pre-edges or, for instance, 2p3D RICs. Also, if you want to understand the DD excitations in 2p3D RICs, then Tanabe Sugano style diagrams are useful. However, they're not terribly informative, since often the units are sort of written out as so. So here on the x-axis, so this is increasing crystal field on the x-axis. So at 0, this would be 0 crystal field. So energy splittings at 0 in x, or in the on the horizontal axis are just due to electron-electron repulsions. And then as you increase DQ, the crystal field splitting, then this is splitting induced due to that crystal field splitting. But our units here are DQ, so the crystal field splitting divided by B, where the B is a Rack electron repulsion parameter, which is directly related to the FK, which I explained before. So using quite slightly different nomenclature. And again, on the y-axis, we're also sort of on this arbitrary scale where we're based on E over B. The states are then labeled in accordance to their symmetry using Mulliken symbols. So really, if we want to use this diagram in order to understand our K pre-edge spectrum, it would be better to plot something like this. So show the energy in electron volts, just have DQ along the x-axis, and calculate this diagram for a particular beta, particular scaling of them, Slater integrals based on Hartree-Fock theory. And then it also would be useful to label, in addition to the Mulliken symmetry labels, also include in that electron occupations. So if we do that, then we can consider for this cobalt ion that I showed before, where we have these 4 peaks, however, with only 2 different 1s electron excitations in the orbital basis, then we can start to understand why we do indeed have 4 there. So if we just add some labeling, so we have the first excitation is an electron going into the T2G. Second excitation, electron into EG. But then we also have these this third excitation, which is if we take our crystal field diagram or at the DQ value here, where it seems to be lining up with experiments, then you can see we have this sort of this avoided crossing with two states that are mixed with respect to each other. So if we are to, at that cut, have a look at how those states are mixed, we can see we've sort of got this. The first state has around 60% T2G5 electron occupation and E2G3, so an allowed transition, where there is also around 34% of this what would be formerly not allowed transition, since we've excited simultaneously an electron between the T2G and EG orbitals, in addition to the 1s electron excitation. However, this fourth excitation is also allowed, since we do have some of this T2G5 EG3 character present. So this means then we can, just based off this energy level diagram, quantify directly the energy splittings and assign the transitions. So the first two, as you can see, split from 0 on increasing DQ, directly relates to the crystal field splitting DQ, parameterized as DQ. And the second pair of peaks, they both have the same symmetry, and they are at this avoided crossing, and the splitting of this avoided crossing is very much dependent on the electron repulsion, and therefore that's gives us this assignment of beta based on the energy splitting between those two. So now we've got some sort of parameterization for DQ and beta and a comprehension of our spectrum. We could then plug that into a ligand-field multiplet software. So here I've plugged it into Crispy, which is which I have details to the website as to where you can download Crispy and conduct tutorials here. Crispy is a graphical user interface for Quanti, the multiplet theory program. And I've also got the link to where you can find more information about Quanti. So I plugged in the value of DQ and beta that I came up with. And then here you can see the simulation nicely reproducing that pre-edge data. Okay, so that was an introduction on how you can understand your K pre-edges, both for the simple case of high spin iron 3+, and then for a more complex example where you have the multiple electronic excitations due to electron-electron interactions. And we were able to quantify both that electron-electron interaction and the crystal field splitting in this case of the cobalt 2+. So what about moving away from octahedral symmetry? So in the next example, I want to consider what happens when we go to lower symmetries. So if we descend from octahedral symmetry down to C4V symmetry, then what we see is a splitting of the T2G orbitals and EG orbitals. So if initially in the octahedral case, we had this sextet A1 high spin iron 3+, as I showed earlier, and in that pre-edge spectrum, we had 2 excitations. If we move to C4V symmetry, then we just have to consider the additional permutations that are introduced by that. So then we end up with in total 4 different excitations due to that additional splitting of the crystal field. But something else happens there. So I showed that spectrum a little earlier, and if we look and zoom in at the pre-edge, you can see spectrum shape changes quite drastically. So it doesn't seem to be simply a matter of just some splitting of the T2G and EG orbitals. Something else is going on. So what's going on here is that we're having a enhancement of intensity due to the non-centrosymmetric coordination environment. So as we go from octahedral to C4V, this allows some 4p z² character to mix into the 3D z². And as I mentioned earlier, the quadrupole part of the spectrum, so this is what we would get if we were to simulate the quadrupole, is very weak. Even just a few percent of 4p character, which would give rise to some dipole type intensity, can drastically modify the spectrum shape. So indeed, this is what happens for this iron 3+. We have some 4p mixing present that enhances the 3D z², resulting in this this large uptake in intensity at that part of the spectrum. So you can see that the role of 4p mixing can both carry important information about large symmetry distortions from octahedral, but also make the interpretation more complex. So what about probing a different edge? So far, we looked at this weak, mainly quadrupole transition, the Capri edge. So if instead we were to target an L23 edge, then we'd be exciting with a dipole transition from 2p into the 3D. And this is also a very good way to access the lowest unoccupied molecular orbitals, or Fermi level. Furthermore, by doing this, as well as having a strong exciton type spectrum, we also gain in energy resolution. And this is due to Heisenberg uncertainty principle, where the core hole, when the core hole lifetime is short, we have a small delta t, and that leads to a large energy broadening, which is here I show a K-pre edge. This is the broadening that we see. In this case, cobalt 3+ low spin, so we have unoccupied EG orbitals only. However, if we come in at a 2p to 3D excitation, much lower energy now, soft X-rays, the core hole lifetime is much longer, and this means that the splitting, the energy resolution or lifetime broadening is narrower. And in this overlay for showing this K-pre edge, it's contrasted against the L3 edge for the same cobalt 3 compound, and you can see a narrowing of the spectrum. Now, to interpret the L23 edge, we need to consider now the intershell Coulomb repulsion and spin exchange, which we could neglect. And this is now because this interaction between the 2p core hole and the 3D shell is now significant. So I will just go over this in one slide, but this part of the talk overlaps with Frank de Groot's webinar, can also be found on YouTube. So let's just step through how we end up with such a complex spectrum shape, for instance, for high spin iron 2+. So that's 3d6. So I'll do this by looking at the different contributions to the spectrum from the Hamiltonian. So if we just consider the crystal field splitting, then we have our ground state with 3d6 electron occupation. We have final states where we can have transitions into the T2G or EG orbitals, split by 10dq, and that would give, in this case, two equally intense peaks, since we have two holes in the EG and two holes in the EG and two holes in two holes in the T2G and two holes in the EG. Then if we were to include spin orbit coupling, of course, the 2p5 has a strong spin orbit coupling around 12 eV for iron. And that splits the whole thing into two. So now we see excitations that come from the 2p half. So this is J equaling a half. So L of 1 minus a half being a half, or L of 1 plus a half being 3/2. So that splitting there is what gives rise to this big energy difference, but it's essentially a multiple, it's sort of a reproduction of what we had going on below when we just considered the crystal field part of the Hamiltonian. There is, however, a perturbation when we include the some 3D spin orbit coupling, and that's the difference between orange and red there that you can see. Then the next part of the Hamiltonian, let's consider the electron-electron repulsions in the D shell. Well, that's very similar to what we saw before with the Tanabe Sugano diagram. So here we're in high spin, so we're down at this point. We expect 3 transitions, which are the bold ones, which I've labeled on the right-hand side. And we've got indeed 3 peaks at the L3 and 3 peaks at the L2. But then you can see when we add to the final part of the model, the interaction between the 2p core hole and the 3D shell, we end up with loads of states. And it's now not really very feasible to try and assign individuals. And that's really where the use of atomic ligand field charge transfer multiplet theory comes into play. And I advise you to check out that YouTube CONEXS seminar to get more information about that. Okay, so coming to the conclusions. So what I would say is we can use for the first row transition metals, the K pre-edge to target electronic structure. I've shown that there is a sensitivity, strong sensitivity to spin state, so whether your system's high spin or low spin, a sensitivity to the valence and number of electrons in the 3D shell, to strong sensitivity to coordination symmetry, although I focus mainly on the case of octahedral coordination environment for simplicity. The pre-edge is sensitive to other types of coordination environments, and I gave an indication of that by looking at the C4V example. There is also this sensitivity to the electron repulsion. Ab initio theories can be good at estimating this. However, by comparing the experiment, one can then scale those Slater integrals to get a more precise quantification of electron-electron repulsion. And that can have implications on covalency, the amount of the delocalization, for instance, of the 3D ions reduces an electron-electron repulsion, and therefore parameterization of the electron repulsion can have an indication on covalency. So I think the big takeaway I want to provide is that in many cases, the pre-edge data comes free along with your XAFS data. So you might already have some data there where you've been neglecting your pre-edge. And I hope this talk inspires you to go and take a little more detailed look at that data to see what additional information might be there that could assist you in modeling your XAFS and having an understanding of both geometric and electronic structure. And then I showed the L2-3 edge for transition metal ions, where you get this improved energy resolution, a more complex spectrum due to the interaction between the 2p and 3D shells, and the requirement of a ultra-high vacuum. And then I also commented on, since the cobalt-2 example I showed was a high energy resolution fluorescence detected K pre-edge, that it's possible to get higher resolution without ultra-high vacuum. And that's a good way to realize pre-edges on compounds which aren't compatible with an ultra-high vacuum environment. Okay, that's it. Thank you. Those are my acknowledgements. I'd like to thank funders and also members of my group. In particular, Miran Huzan. Miran and I have been working recently on the use of Tanabe Sugano diagrams for interpretation, mainly actually of 2p 3D RICs, but they also serve well as in the talk today for interpreting K pre-edges. And we're putting together a tool that enables to do this type of analysis I talked about today. While the Tanabe Sugano diagrams are useful, I think if you're wanting to compare to experiment, it can be better to be able to calculate your own as a function of dq or as a function of beta, and be able to take cuts to actually infer directly what the electron occupation is of the individual states in order to determine whether they're transition allowed for the pre-edge or the 2p3d RIC. So we don't have anything up yet on our group website, but we will put something up sometime soon. So if you're checking this out on YouTube, there's a good chance that it will be there. But for those that are listening live, give us a couple of weeks. I also showed some actual spectrum simulations which were conducted using Quanti, using the CRISPy interface, and I advise you, if you're interested in simulating K pre-edges, L edges, or all kinds of X-ray absorption, emission, RIC spectroscopy, then you check those out. That's all. Thank you very much.
Brilliant. Thank you very much, Mike, for a really great talk. I think it should inspire a lot of people, if they haven't looked at the pre-edge, to look into that region. So we've got time for a few questions now. So as I said before, you can either type them in the chat, and I'm kind of looking at the chat. Also, if you want to ask a question yourself, you can either turn on your camera or your mic, or you can raise your hand. So lots of options. So just while potentially people type, there's always a small delay with online webinars. So you mentioned about kind of calculating the electron-electron repulsions from first principles. Yeah. And then tuning them or scaling them so that the spectrum matches experiment to kind of get that interpretation. Is there any particular rule that you use in terms of, because obviously when you have these free parameters, you're free to scale them as much or as little as you like, and then it can kind of move away from interpretation. So or physical meaning. Do you have any kind of rules on kind of how you scale these, or does it come from experience? Yeah, well, these are free parameters, but they have a direct physical meaning, right? So this means that any scaling is in a truss region reflective manner, yeah, that somewhat comes from experience, but there is a rule of thumb, and ultimately the use of multiplet theory for the calculation of absorption spectra, for instance, has been benchmarked to Hartree-Fock theory in terms of the Slater integrals. And the Slater integrals are known to overestimate their strength by around 80% relative to free ion value. So one starts off at 0.8, a scaling of 0.8. And that would then reflect a completely ionic system. And then if you are to consider, and I mentioned this briefly, the effect of metal ligand covalency, which you can, in a sort of hand wavy picture, consider the delocalization of the 3D electrons as they are expanding out over the molecule or the local coordination environment around your absorber. This then reduces that DD interaction, for instance, and then you can consider that beta value decreasing further and being something then like decreasing somewhat below 0.8, so a scaling of 60 to 0.6 or something like that could be feasible. So yeah, there's quite a restricted range for which the value can take. I think how you do that and how much you vary things depends on the resolution of your data. So if you have really high resolution data, it's not really a problem. If you don't have very high resolution data, you can probably just leave it at scaled at 0.8 of Hartree-Fock theory. Okay, cool. Thanks very much. So there's a question in the chat from Rory Cohen, so I'll just read it out. Says, thanks very much for the talk. You mentioned using L3 edge spectra for transition metals further down the block. Do the principles you've outlined K pre-edge apply to the L3 edge? Well, yeah, so of course you always need to just keep in mind what your, depending on the valence, what the electron occupation is.
And if you have, for instance, an unoccupied 4D shell, for instance, and you're wanting to access the L edge, then things can be a little bit more complicated, since there you don't have such a sharp exciton. Now, if you were to want to understand more about the simulation of heavier, for instance, 4D ions, I think some of the webinars, some of them, there have been some relevant, not webinars, but the actual workshops, for instance, as part of CONEXS. Tom, for instance, FDMS, use of FDMS, for instance, and I think that those are available on the website. Recorded talks and exercises and stuff. I'd advise to check that out.
Okay, are there any other questions? I don't see any at the moment. So if not, we can thank Mike again. And it's always hard when everyone's got their mic off, but so I still haven't got used to that with online. So yeah, thanks very much again, Mike. I'll now